Let's walk through Activity 9, where we explore interactions with categorical variables as predictors in a regression and introduce the logistic regression framework for predicting a y variable that is categorical with two levels, like a yes or no response. So question 1 is going to ask us to explore interactions involving categorical variables when being used as predictors in a linear regression. Now the data file we're going to use is one you have to download off of Blackboard, and it's act9-wholesale.dat. So the first thing you're going to do is to read in the data file using the read.csv command. Now when you run this, one thing you want to make sure is that both this RMD file and the data file are actually in the same folder. You can check to see where the RMD file is located by looking at the path in the upper part of the console window. Very often what ends up happening is that you automatically load up your RMD file from the downloads folder, and so it'll be thinking that you're looking inside that downloads folder for everything else. So make sure that you've just moved over that RMD file over to the BAS320 folder that you're using, and make sure that data file is in there as well. Okay, so this data frame has 8 different variables in it, 440 observations. And basically what it's looking at is customers to some company, a wholesaler, that sells products typically used in the food industry. So consumables, groceries, detergents, etc. And there's 2 broad types of customers that this company has, restaurant customers and retail customers. So we might be interested in using the type of restaurant as a predictor into how much sales in each of these types of products we might be getting. And then also there's a variable called region. This data is from Portugal. And this discusses where that customer is located. So let's consider making a model that's going to predict the annual spending of fresh vegetables, fresh from the annual spending on other products here. So all right, let's talk about how we do this. So part A says to fit the multiple linear regression model, predicting fresh from all other variables. So we can do this just using our standard way. I'll call my model M, and since the variable we want to be predicting is fresh, that goes on the left-hand side of the twiddle. And we can do twiddle dot because we're going to use all of the predictors in the data set to help in our modeling. So we say the name of the data frame, in this case I called it whole. And it asked us to look at a summary of the model, so we can get the coefficients out. And then it also asks us to include the results of drop 1. Now with drop 1 I need to add in test equals f, and drop 1 helps to conduct a significance test for a multi-level categorical variable with 3 or more levels. We know the p-values from the summary output don't really tell us what we want to know. All right, so question A1 says that this regression lets us answer the question, is there a difference in the average amount of money spent on fresh vegetables between otherwise identical retail and restaurant customers with respect to all the other variables in the model? So what number in the regression output answers this question? Well, one thing that we do remember about categorical variables as predictors is number 1, they're represented by an indicator variable that either equals to 1 or 0 depending on what level we're talking about. And in this case, since the type of customer only has 2 levels, restaurant and retail, restaurant is the reference level because it comes first alphabetically. Retail is going to be appended to the name of the column in the data frame. That's the way R does it. And so this is our indicator variable representing the type of customer that we're discussing. Now we've talked about what the coefficient of the indicator variable tells us, and it tells us something really quite interesting. It's telling us the difference in the average value of y among otherwise identical customers when one customer has the type, whatever the level is appended to the name of the variable here, and the other type has the reference level that ever comes first alphabetically. So actually this coefficient, about minus 4,000 here, is telling us the difference in the average value of fresh between otherwise identical customers here. Same region, same expenditure on milk, grocery, frozen, detergents, and meat. And the only thing they differ is in the type of customer they are. And this is retail minus restaurant. So what number in the regression output answers this question? Is there a difference in the average amount? Well, the answer is, we estimated there's a $4,000 difference. We need to know if that difference is statistically significant or not, and we answer that by looking at the p-value here. So when an indicator variable is statistically significant, that's telling you that there is a statistically significant difference in the average value of y between that level and the reference level after accounting for the other variables in the model. In other words, assuming those individuals are otherwise identical. All right, so we do see a statistically significant difference. There is a statistically significant difference in the average value of fresh. P-value is 0.019919. And it looks like retail customers spend on average $4,000 less than restaurant customers. This is the reference level. And that makes sense. You know, if you're a restaurant, you're buying a lot of food, a lot of fresh produce, you're going to be spending a lot more than a retail customer. All right, question A2 says that the regression also allows us to probe where the average amount of money spent varies based on the location of otherwise identical customers. I guess really should be weather here. And so the way that we can look at this is by looking at the coefficients of the variable region. Region has 3 levels. It has Lisbon, Oporto, and other. Lisbon comes first alphabetically, so it's the reference level. The other levels get their own indicator variables. This variable here, region Oporto, equals to 1 if that customer lives in Oporto and 0 otherwise. All right, and we're being asked, is the difference in the averages between regions statistically significant? And if so, which region has the largest average? Well, if we only had 2 levels here, we could just hone in on the p-values because that's telling us the difference in the average values of y between levels. Now, with the categorical variable with 3 or more levels, this p-value is telling me something a little bit too specific. It's commenting on whether there is a statistically significant difference in averages between the level this indicator variable represents, in other words, Oporto, and the reference level. So this is just a comment saying that no, there's no statistically significant difference in averages between Oporto customers and Lisbon customers, but our question's more general. We want to know if there's any difference in the average value of y between any 3 of these regions. And so that's why we have the drop 1 command. The drop 1 allows us to see whether or not a categorical variable with more than 2 levels is statistically significant. So we can look at region, and we see a 2 next to this being indicative that there are 2 indicator variables representing region here. And to know whether or not there is a statistically significant difference in averages, we look at the p-value in the drop 1 test. In this case, we see that it's bigger than 5%. So as a predictor, region is not statistically significant. The implication is that there is no statistically significant difference in the average value of y between regions when we compare otherwise identical individuals in terms of customer type and values for these other variables. So what we say is that there is no statistically significant difference in averages between regions because the p-value of the effect test in drop 1 is 0.25468, bigger than 5%. The implication of the categorical variable not being significant is that the difference in averages between levels is not statistically significant either. Okay, so we do see a statistically significant difference between otherwise identical customers when one lives, or one is a restaurant customer, one is a retail customer. We do not see a difference in where these people live, basically. The same average value of y, same average value of fresh, regardless of region. All right, so this was a fairly simple model. We straight up just tried to predict the value of fresh from a weighted sum of the predictor variables. And we've seen that very often interactions between variables play an important role in relationships. So the model we just fit may be overly simplistic because it completely ignored the possibility that there are interactions going on between the variables. So without interactions, the model is going to assume that the difference in the average value of y, when we compare these otherwise identical individuals who just differ in one particular variable, is a constant. It's the same magnitude of a difference regardless of what the other characteristics of those individuals actually are. So we'd like to probe, all right, are interactions important here? So going back to our I guess we haven't looked at that quite yet. So, all right, let's continue onward. Let's consider the interaction between milk and type. All right, so type is our type of customer, restaurant versus retail. We saw that there was a difference in average value of fresh between those two types. Maybe there is an extra bit of this story. Maybe the size of this difference, the strength of the relationship between, say, fresh and milk depends on what type of customer we're talking about. So if we include the interaction between these two variables, it allows us to do two things. Number one, it allows us to allow for the possibility that the strength of the relationship between fresh and milk might be different between customers. And it allows us to model the possibility that maybe sometimes the difference in fresh might be big between the two types of customers, and sometimes it might be small, depending on the types of customers, and it all depends on what value of milk. Without that interaction, we assume a same constant difference between the customer types. Okay, so let's fit that model, and it's easy enough to do. We're going to predict fresh from milk and type and their interaction, and I can get both predictors along with their interaction by just having a multiplication symbol in between those two predictors. And the data this lives in is whole. What we're going to do is visualize the model with the command visualize model. And in this case, it helps to actually put the legend in the bottom left here. So I'm going to put bottom left as a second argument. And then we're going to look at a summary of the model. All right, fit it, look at it, look at the numbers. All right, so we know that when we have a categorical predictor in a regression, in effect, each level of that categorical variable gets its own regression line. Without an interaction, both of those lines are parallel to one another. The difference in intercepts, the vertical offsets between lines, encodes the difference in the average value of y between levels. When we do have an interaction, well, still every level of that categorical variable gets its own regression line, but now these lines can have different intercepts and different slopes. So we're allowing the strength of the relationship between fresh and milk to potentially be different between retail and restaurant customers. All right, so we're asked which type of customer has the stronger relationship between fresh and milk. Well, we see both customers have a positive relationship between fresh and milk, but this black line definitely has a steeper slope than the red line. And the strength of relationship is indicated by how steep that slope is. And so we can say that the strength of the relationship for restaurant customers is much stronger than the strength of the relationship for retail customers. So the relationship between fresh and milk is much stronger for restaurant customers than retail customers. It has a much steeper slope. So, all right, just due to the nature of collecting data and chance variation, we never expect the lines to be exactly parallel. We expect there to be a little bit of a difference in slopes. The question becomes, is the difference in slopes statistically significant? Is the difference in strengths of the relationships really different between restaurant and retail customers? Well, we can answer that question by looking at the p-value of the interaction variable in the model. So here's our interaction variable. There's always going to be a colon separating the two variables involved in the interaction. And what we see is that the p-value is less than 5%. So that indicates that the interaction is statistically significant. The implication is that yes, there is a statistically significant difference in the strengths of the relationship depending on what type of customer we're looking at. So the difference in strengths is statistically significant because the p-value of the interaction term is 0.00369, less than 5%. The implication of the interaction variable being statistically significant is that the difference in slopes / strengths is also statistically significant. So interesting. Not these two types of customers don't behave quite the same. The nature of the relationship between fresh and milk looks to vary between them. One group has a stronger relationship than the other. All right, now we're being asked to consider the interaction between detergents and region. All right, so what does that allow us to do? Well, if we put in interaction between these two variables, number one, it allows us to model the possibility that perhaps the strength of the relationship between fresh and detergents is different depending on what region we're focusing in on. So let's go ahead and fit that model. I'm still going to call it M. We're still predicting fresh. And I can do just twiddle detergents times region to get both variables in and the interaction variable. Now, region is a 3-level categorical variable, so it's actually being represented by 2 indicator variables, so we actually are going to have 2 interaction variables as well. So let's go ahead and visualize this model, putting that legend in the bottom left. I can just copy and paste here, and then we can get a summary of the model, and we can also run drop one. I'll explain why in a second. Okay, so let's fit the model. Fit it, look at it, and get some numbers out. All right, so what the scatter plot is showing us is that there's a negative relationship between fresh and detergents regardless of what location we're focusing in on. And it does look like the strength of the relationship between fresh and detergents may vary between region. It looks like this black line has the steepest slope, the most negative slope, whereas the green line has the slope that is closest to 0. So the relationship looks to be strongest for customers living in Lisbon, and it looks to be weakest for customers living in the other region here. So the strength of the relationship looks to be the strongest for Lisbon customers, steepest slope, farthest from 0 at least, while the strength is weakest for other customers. Slope is closest to 0. So once again, we don't expect the slopes to all be identical between levels. Just from this sheer act of collecting data and chance variation, we expect there to be a little bit of a difference in strengths. The question becomes, is the difference statistically significant? Now, if there were only 2 levels, we could look at the p-value of the interaction variable to answer that question. But when we have more than 2 levels, this p-value is being overly specific. It is answering the question, is there a statistically significant difference in strengths of the relationship between fresh and detergents when we compare customers living in the Oporto region to the customers living in the reference region, the Lisbon region here. So these 2 p-values are basically telling you that there's no statistically significant difference in strengths between Lisbon and Oporto and Lisbon and other. But we want to know if there's any difference overall. What about Oporto versus other? That's where drop one comes in, because drop one can test the interaction as a whole. So the output of drop one is telling us that as a whole, the interaction between detergents and regions is not statistically significant. The p-value is bigger than 5%. The implication of this is that there is no statistically significant difference between any 3 of the levels of region. So although we do see a pretty noticeable difference in slopes here, it looks like this difference is readily explainable just by chance variation and the sheer act of collecting data. All right, so we see that the difference in slopes is not statistically significant since the set of interaction variables is not statistically significant. The p-value of the effect test for the interaction is 0.3163. All right, so the strength of the relationship looks to be the same regardless of what region we're focusing in on. All right, B3 asks us to fit a more complex model here. It asks us to fit a model predicting fresh from frozen, from region, from milk, and the interaction between region and milk. So one thing I could do is I could actually just type that in, kind of be redundant, region times milk, but I can actually be a little bit clever and just put in region times milk as the predictor here. So this will predict from frozen, from region, and from milk, and then also with the interaction between region and milk here. All right, so what we're going to do is we're going to start out with a summary of this model and then actually write out the implicit regression equations for the 3 regions that we're focusing in on. So we're asked to write the implicit regression equation predicting fresh from frozen and milk for customers in the Lisbon and for customers living in the Oporto region. So for my response, I'm always going to start out with the overall regression equation, and in this case we're predicting fresh, and we just read down the numbers. The intercept is 10,000 essentially, it's kind of rounding that, plus 0.9 times frozen, Then we get a minus 2600 times region of Porto. Then about a minus 1600 region other. Then about a minus 0.37 times milk. Then a plus 0.06 region of Porto times milk term. It's getting long, so I'm going to expand this. Plus a 0.05. This is going to round down to actually just 0.5 here. 0.5 times region other times milk. Okay, so that's my overall regression equation. Now, if I want to write out the implicit regression equation for a particular set of customers, all I need to do is plug in values for the characteristics that I know. So in this case, I'm interested in writing out the implicit regression equation for customers in Lisbon. All right, well, Lisbon comes first alphabetically of these three levels, so it's the reference level. What that means is that region of Porto and region other are 0, wherever they appear in the regression equation. So for Lisbon customers, I'm just going to go ahead and copy and paste the regression equation and just plug in 0. For region of Porto, I'm going to plug in 0. For region other, and I have that here as well, times 0 times milk, region other times 0 times milk. And what's nice is that this is a 0, that's a 0, that's a 0. Oh, no, that's not a 0. We still have a minus 0.37 milk. But these two numbers are 0 as well. So in fact, my equation can be reduced down to just fresh is equal to 10,000 plus 0.9 frozen minus 0.37 times milk. And that's it. Okay, now what about for Oporto customers? So for Lisbon customers, we had region Oporto equals region other equals 0. Well, for Oporto customers, we're going to have that the indicator variable region Oporto equals to 1, but region other is still equal to 0. So basically what we'll do is we'll just copy and paste our overall regression equation and plug in the relevant quantities. 1 for region of Porto, 0 for region other, wherever we see them. And then we're going to simplify. So what's nice is that the zeros immediately go away. Can ignore those. And then 0.06 times 1 times milk, well that's just 0.06 times milk. Minus 2600 times 1, well that's just minus 2600. So all I need to do is group the terms. I have a 10,000 minus 2600, that's 7,400. I have a 0.9 frozen, and keep that as is. I've already taken into account that term. Then I have a minus 0.37 milk and a plus 0.06 milk. Well, that combines to be minus 0.31 milk. So there we go. All right, part C asks us to fit a model suggested by the boss, where we predict fresh from all other variables, along with the interactions between region and frozen, region and detergents, and grocery and meat. All right, so I've already done the shortcut for you. This is the model that we want to fit. And question C1 asks us to verify that the interaction between region and frozen is statistically significant. Well, we know we have to use drop 1 because region has more than 2 levels. So we can go ahead and look at a summary because we're being asked to, and then look at the results of drop 1 using that partial F test. And so here's one thing that's kind of funny and kind of indicates why that effect test and drop 1 is really quite important. If we do look at the interaction between region and frozen, and we look at these p-values here, we see that both of these p-values are bigger than 5%. So when we compare Oporto to Lisbon, no statistically significant difference. When we compare other to Lisbon, no statistically significant difference. But when we look at the interaction as a whole, region times frozen, we do have a statistically significant difference between at least 2 of those levels. So it's most likely the case that, all right, if Lisbon was essentially the same as Oporto and the same as other, it must be the case that Oporto and other are different from each other. So the interaction is statistically significant since the p-value of the effect test is 0.003155, much less than 5%. So at least 2 regions have strengths of the relationship between fresh and frozen to vary in strength. And based on the analysis, it's pretty clear that it's Oporto and other here. All right, C2 asks us to kind of look at some of these interactions. There's a lot of them in here with the command C interactions. So what I'm going to do, since this is a lot of plots, is I'm going to make my plotting area quite a bit bigger here and run C interactions. Spelling it correctly. All right, so the top left plot is showing us the interaction plot between frozen and region as we're studying the relationship between fresh and frozen. So this is telling us kind of what we just examined here. It does look like there is a difference in strengths between the relationship between fresh and frozen depending on what region we're looking at. The individual p-values in the summary was basically telling us that there wasn't any statistically significant difference in the lines for Lisbon and other. So the green and black lines look to be about the same. And also the black and the red lines look to be about the same because the p-value of that interaction variable was bigger than 5%. But the results of the effect test tells us that, okay, but there is some difference overall. So it must be that the green and the red lines look to be statistically different in strengths here. All right, so there we go. We did determine a statistically significant difference in the strengths of these relationships. It looks like the strength of the relationship between fresh and frozen is strongest for other customers and weakest for Oporto customers. Strongest because it's steepest, weakest because it's closest to 0 here. All right, these other interaction plots explore other aspects of that problem. This is breaking down the relationship between fresh and grocery depending on what the meat expenditure of the customers were. And it's basically showing you that, the strength of the relationship between fresh and grocery isn't a constant. It depends somewhat on the amount of money that customer is spending on meat. When the customer spends a lot on meat, okay, the relationship between fresh and grocery is fairly weak. If they're not spending much on meat, the black line here, the relationship is really quite strong between fresh and grocery. So it's kind of telling us some interesting aspect about this relationship that we probably need to take into account, but we'll leave it at there. All right, question number 2 asks us to get our feet wet with logistic regression. Basically what we're going to do is read in the data set called Reacquire. And what's interesting about this data set is it has information on customers that were with the company for a while but then churned. They left, they stopped being a customer. The company tried to intervene and gave them a special offer and said, hey, come back and you'll get maybe 15% off your next order. And then they kept track of whether or not the customer was indeed reacquired. So we want to predict whether the customer was reacquired or not based on some of the information about that customer. So in this case, the value that we want to predict is a categorical quantity here. It's either a yes or a no. And so we need to have logistic regression help us out. We're going to predict the probability that a customer will or will not be reacquired here. And then we can convert that into levels after the fact. All right, so the levels of reacquire are yes and no. What the logistic regression does is choose one of those levels to model, basically. We're going to predict the probability for one of those levels. Which one do we actually end up predicting? Well, we call that the level of interest, and the level of interest is always going to be the one that comes last alphabetically. So the logistic regression will predict yes, because that is last alphabetically. So the logistic regression is going to call yes our level of interest. And in fact, that's really what we're interested in, the probability of being reacquired. So that works out nicely for us. Part B says to fit a simple logistic regression model predicting reacquire from lifetime 1, basically the amount that the customer spent before they churned in the first time. So I'm going to still call this M. To do logistic regression, we actually need a different command. We need glm instead of just lm. And the syntax still works the same, which is nice. We want to predict reacquire, and we want to be predicting it from lifetime 1. Data equals to reacquire. And to turn on logistic regression, we need to make sure to pass the additional argument family equals binomial. And what we'll do is we'll get a summary of the model, and let's actually just look at this model. So we fit it, we look at it, and talk about it. All right, do customers who have spent more money before churning have a higher or a lower chance of being reacquired than customers who have spent less money? All right, well, here is our model. We're predicting the probability of yes being reacquired. And what we're seeing is that this curve kind of goes upwards in a nonlinear fashion, indicating that customers with larger values of lifetime 1 have a higher probability of being reacquired. So we see customers who have spent more, larger values of lifetime 1, have a higher probability of being reacquired. Okay, so that's pretty easy to just read from the graph specifically, but we could also get that from the summary of the model here. So if we look at a summary, what part of the output tells us that indeed the probability of reacquiring changes with lifetime 1 in the same way we saw from the plot, that it's basically customers with larger values of lifetime 1 have a higher probability of being reacquired. Well, the coefficient of the predictor variable tells us all we need to know. Now, with logistic regression, the actual value of the coefficient doesn't really tell us anything immediately useful. Instead, it's the sign of the coefficient that clues us in to how the probability differs between individuals. Because this is positive, it's telling us that customers with the larger value of x, in other words, the larger value of lifetime 1, are going to have the higher probability of the level of interest. And since the level of interest is yes in this case, the fact that this is positive means that it's consistent with the curve that we're seeing here. So the coefficient of lifetime 1 is positive, so customers with, or who have spent more before churning have a higher probability of being reacquired. That kind of makes some logical sense, so it's nice the data supports that. Part D asks us to use the numbers from the summary of the model and to figure out what value of lifetime 1 there's a 50-50 chance of reacquisition. So it turns out there's just a way to get this number out. We can take the intercept term, divide by the slope, we'll call it the slope, it's not really a slope, and then do that times minus 1. This quantity actually tells us the value of x at which there's a 50-50 chance of observing each level. So in this case, what we see is that a value of lifetime 1 of 328 would give a 50% chance of reacquiring, 50% chance of not being reacquired. Does that look reasonable? 328 is right about here. Boop, boop, it's right at about 50%. We can kind of confirm that. We can ab line v equals draw a vertical line at 328. We can draw a line at 0.5. Bam, calculations are great. All right, part E asks us to write out the equation for the logistic curve, then predict the probability that a customer that spent $400 before churning would be reacquired. Okay, so this is a bit of math. Our equation is that the probability is equal to E raised to the B0 plus B1 times x power divided by 1 plus E raised to that same power. Now we need to be a little bit careful how we write that in R. I'm going to comment that out because I would freak out if I tried to run that as a command. So to take E and raise it to a power, I actually need to do exp and then in parentheses, put in parentheses what I want to be raised to that power. So B0 is that intercept term. I can copy and paste this value, plus B1, which is the quote-unquote slope, this number right here, times our x value, which is 400. That's the top part of the fraction. And I'm going to save some time. I'm going to need to use that again. So I take that, divide that by 1 plus e raised to the same number, copy and paste that guy, run it, and what we find is that the model predicts a 64% chance the customer would be reacquired. What about the probability the customer will not be reacquired? Well, luckily those two probabilities add up to 1. So if I just do 1 minus this number, that'll give me not reacquired. So reacquired, the probability is 64% according to the model. Not reacquired would be 1 minus that. And we can just run that to see what that would be, about 36%. All right, now we want to fit a simple logistic regression model predicting reacquire from offer. the value of the offer used to entice the customer back. So data equals to reacquire, and I gotta add in family equals binomial to turn on logistic regression. All right, so let's fit it. And so let's figure out what I possibly have done. Oh, because no. Oh, so you guys will make this error too. See, I've been doing this for 10 years and I still make errors like this. So LM is for linear regression, GLM is for logistic regression. So there we go. Fit it, visualize this model. And if we visualize it, actually it just looks like kind of a straight line. So it's always a logistic curve that's actually being fit, but sometimes we're looking at that logistic curve at such a small range that it actually appears to be a straight line. So one thing we can do is actually change the x limits, the horizontal limits of that model, by passing in the argument xlim equals and then putting in the lower and upper limits. And this way, we can see that indeed we did fit a logistic regression model. Now, values of offer that are negative are impossible. Values that were bigger than 20 or 40 don't ever happen in the data, but it shows you what the model looks like at other values. Okay, so there's really no comment to put there. We're fine. Finally says it's a bit naive to study the relationship between the probability of reacquiring a customer and the amount of money spent before churning with a simple logistic regression, because there's a lot of other reasons why the probability of being reacquired could vary from customer to customer. It's not just one thing. Maybe it's a combination of these factors. So let's go ahead and fit a more detailed model where we predict reacquire from, what are we asked to predict from? From lifetime 1, as well as offer, and lapse, and price change, and gender, and age. So that's going to be in the reacquire data frame, and the family is going to be equal to binomial, and we'll get a summary of this model. And it looks like I botched this command because you'll notice it changed to a plus sign, indicating it doesn't like something about that last line I just ran. So I'm going to press escape a few times, and I see there's a rogue back quote there, so I'll take that out. Lifetime 1. Summary of that model. All right. So a multiple logistic regression model allows us to do something similar to multiple linear regression, basically compare otherwise identical customers that only differ in one particular quantity of interest. So among otherwise identical individuals, does the individual with the larger value of lifetime 1 have the larger or the smaller probability of reacquisition? Now, the simple logistic regression said that customers with the larger value of lifetime 1 had the higher chance of being reacquired. Is that still true after we compare more identical customers, customers that are otherwise identical in terms of age, gender, price change, lapse, and offer? Yes. It looks like the coefficient of lifetime 1 is still positive, statistically significant, and so that implies that among otherwise identical customers, the one that spent more before churning is going to have the higher probability of being reacquired. So the customer that spent more before churning, higher value of lifetime 1, has the higher probability of being reacquired. Coefficient of lifetime 1 is positive, and the predictor is statistically significant. All right, there we go. We're good, and hopefully that'll help you out with the homework.